Hello student, welcome to our fourth lesson. In this lesson, we are going to look at conservation of linear momentum. We start with the law of conservation of linear momentum. And this law states that for a system of colliding bodies, their total linear momentum is constant, provided no external forces are acting. Now note the key words here. We have for a system of colliding bodies. Then we are talking of the total linear momentum is constant and provided there is no external force that is acting. That is what we call the law of conservation of linear momentum. In other words, this law we are going to see that the momentum or the linear momentum before the collision will be equal to the linear momentum after the collision. So if a body of mass A or if a body A of mass m1 initially moving with a velocity of u1 collides linearly with a body B of mass m2 initially moving with a velocity u2 and their velocities after collision are v1 and v2 respectively, then we can say that the total linear momentum before impact is equal to the total linear momentum after impact. And the momentum is given by the mass times velocity. So when we talk of the momentum before the impact, we are going to refer to the initial velocities, which implies that because there are two bodies there, we can consider the momentum due to the body A and the momentum due to the body B. This will give us m1 multiplied by u1, that is momentum for the first body, then m2 multiplied by u2, you add the two, this is the momentum of body A and this is the momentum of body 2 or the body B. Then after collision, they attain a different velocity which we call the final velocity v1 and v2. So the body A will have m1 v1 as the final momentum and the body B will have m2 v2, which is our final momentum. And because we are saying that the momentum is conserved, then it implies that the total momentum before impact or before the collision is equals to the total linear momentum after the collision. And that is how we are saying m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. We look at an example. A body A of mass 5 kg moving with a velocity of 3 meters per second collides head-on with another body B of mass 4 kg moving in opposite direction at 6 meters per second. If after collision the bodies move together, calculate the common velocity. We proceed as follows. We take the momentum directed to the right to be positive, and therefore the other one that is directed to the left will be negative. So momentum of A before collision is mv. Or in other words, we are talking of mu. So it will be 5 times 3, you get 15 kilogram meters per second. Then the momentum of B before collision, the velocity was 6 meters per second. And because it is moving in the opposite direction, then we take that to be negative. So it will be 4 times negative 6, you get negative 24 kilogram meters per second. So this is momentum of A before the collision and momentum of B before the collision. So momentum after collision, remember now the two bodies are merging and becoming one. And therefore, we have to add the mass and then we multiply by the common velocity. The mass is 5, then we add for the B, which is 4, you get 9v. That's how we are getting now the momentum after collision. So the momentum before and after must be equal. So we have to add the momentum before. That is the momentum for the A, which is 15, plus the momentum for the B, which is minus 24. When you add, you get negative 9, and this is 9. So by dividing by 9, you get that the final velocity or the common velocity will be negative meters per second. Remember, this negative is just showing us the direction, which implies that after the collision, the bodies will move towards the left direction. In other words, they will move towards the direction where the mass B was moving. That's why it is negative. The negative sign shows the direction. Then from there, we can go to the types of collision. We have several types. We start with the first one, which is elastic collision. Now, in this collision, we have that both kinetic energy and momentum are conserved. That is, if the bodies 1 and 2 above collide elastically, then this one momentum is conserved, which implies that momentum before the collision is equal to the momentum after the collision. We are also saying that the kinetic energy is conserved, which implies that the kinetic energy before the collision is equal to the kinetic energy after the collision. And for you to get the kinetic energy before the impact, you use the initial velocity. You know kinetic energy is given by a half mv squared. But because we are considering the kinetic energy before the impact, then we use the initial velocity, which is a half mu squared. That is for the first body. Then the second body, you have a half m2u2 squared. Then after colliding, these two bodies, they acquire different velocities, v1 and v2. So again, you get the kinetic energy for the first one and the kinetic energy for the second one. And for the elastic collision, this energy should be equal to the final energy or the kinetic energy after collision. Note that in this collision, bodies separate and move in the same or different directions after collision. So in this case, the bodies they don't merge together. After colliding, they move in different direction or they can move in the same direction, which implies that the velocity after the collision is different for each body. Then number 2, we have inelastic collision. Now this is a collision in which momentum is conserved, but kinetic energy is not conserved. So note the difference. In our first case, both kinetic and momentum were being conserved. But when we come to inelastic collision, only momentum is conserved. What happens to the kinetic energy? Why isn't it not conserved? We are going to see that due to collision, in this case, the colliding bodies fuse together, they become one, and they move together in one direction with a common velocity, like the example that we have just done. So during this collision, we are saying that the kinetic energy is not conserved because most of the energy is converted. The kinetic energy is converted either to heat or to sound or even to light. That is why kinetic energy is not conserved. So if the collision of two bodies, 1 and 2 above, collide inelastically, then we have that m1u1 is plus m2u2 is equals to m1v1 plus m2v2. The momentum is conserved, but kinetic energy is not conserved. That is why we are saying a half m1u1 plus a half m2u2 squared is not equal to a half mv1 squared plus a half m2v2 squared. In other words, the kinetic energy before collision is not equal to the kinetic energy after collision. Kinetic energy is not conserved. From there, we can look at another point where we are saying that the total kinetic energy after the impact is always less than the total kinetic energy before the impact, and the loss of kinetic energy is due to 1, energy is used in deformation of the bodies. Remember, they are fusing together, and through that fusion there is deformation. So some of the energy is used in that deformation of the bodies. Then other energy is transformed to heat, sound, and light. And that is why now the total kinetic energy before and after are not equal. We look at an example. Two trolleys of masses 2 kg and 1.5 kg are traveling towards each other at 0.25 meters per second and 0.4 meters per second respectively. The trolleys combine on collision. Calculate the velocity of the combined trolleys. And number 2, in what direction do the trolleys move after collision. We proceed as follows. We have the diagram that is showing us the two trolleys. You have this one is moving towards this direction and this one is moving towards the opposite direction. Note that we have put this as the negative so that we can show that it is opposite of the first velocity. So we proceed as follows. The total linear momentum before impact is equals to the total linear momentum after collision. So our momentum before will be m1u1 plus m2u2. But after collision, they are combining, and therefore, the total mass will be m1 plus m2, then multiplied by velocity. Then after that, we substitute the values. We have that the velocity for the first one, or the mass m1, is given by 2 kg multiplied by 0.25. Then from there, we have 1.5 multiplied by 0.4, which is negative. Then after that, remember we are saying that this is 2.5, that is the mass. The velocity is 0.25. The mass is 1.5. The velocity is negative 0.4. That is what we have substituted in this value. Then after that, after they combine, the masses fuse together. So the mass will be 2.5 plus 1.5. Then you multiply by the common velocity. When you add all these, you will get that the value here will be 0.025. And then you divide by 4, which is the sum of this. You get that the velocity will be 0.00625 meters per second. This is the velocity that is gained by the two trolleys. But if you look at this velocity, it is positive, which implies that they will move. Both of them after fusing, they will move in the direction to which trolley of mass 2.5 was moving, because that trolley is the one that has a positive velocity. Then from there, we move to another example. A bullet of mass 20 grams traveling horizontally at a speed of 50 meters per second embeds itself in a block of wood of mass 1,980 grams suspended from a light inextensible string. Find number 1, the velocity of the bullet and block immediately after collision. Then number 2, the height through which the block rises. We proceed as follows. We have the diagram. This is the bullet and this is the block. As it strikes, this will embed. It is inside the block and therefore they swing. So we want to get this height and we also want to get the velocity. So we have that the momentum before collision must be equal to the momentum after. And before, we are taking the mass of the bullet multiplied by the velocity of the bullet, then plus the mass of the block multiplied by the velocity of the block, and that will give us now the momentum after, which is mb plus mw multiplied by the common velocity. We substitute the values. Remember, the mass is given in grams, so you have to convert that into kilogram by dividing through by 1,000. And this will give you 0.02, then multiplied by the velocity, which is 50. Then this again, you divide by 1,000, you get 1.98, multiplied by the velocity, which is 0, because this block was resting. Then after the collision, the two become one. You can see in the diagram. The bullet is inside the block. So the total mass will be 0.02 plus 1.980 multiplied by the velocity. Now this will cancel out because anybody or any value multiplied by 0 becomes 0. And therefore, when you multiply this, it will become 1. And this value will be 2v. Then from there, it becomes our v, you divide through by 2, our v will be a half, which is 0.5 meters per second. Then we are supposed to get the height through which the block rises. We know that at maximum height, all kinetic energy is converted to the potential energy. And the kinetic energy is given by a half mv squared. And the potential energy is mg height or mgh. The masses will cancel out because they are common. So we are left with a half v squared is equals to gh. And our v is 0.5. So it will be a half times 0.5 times 0.5, which is equals to 10, that is our G, multiplied by height. So from here we can say that our height is 0.125 divided by 10. You get that our height is 0.0125 meters. Then from there, we move to some application of law of conservation of momentum. We have rocket and jet propulsion. We have that a rocket propels itself forward by forcing out its exhaust gases. You know, this one, it is propelling itself forward. How does it do that? It forces the exhaust gases out. These hot gases are pushed out of the exhaust nozzle at high velocity and gain momentum in one direction. Then the rocket also gains an equal but opposite momentum in the opposite direction. Remember, the momentum before is equal to the momentum after. So the gas will move with the momentum and the rocket will also gain a momentum. And that momentum, the rate at which the momentum changes, will provide the forward force that will force now the rocket to propel. Then we have the garden sprinkle. In this case, the pressure of the water inside the pipe causes the water to be ejected through the nozzle at high velocity. Now, the ejected water gains momentum. Remember, momentum is mass times velocity. So whenever we have velocity, then there is momentum. So ejected water gains momentum and causes the sprinkle to rotate, as shown in this diagram. So in other words, we are saying the water is coming out due to the pressure inside the pipes. The water, as it comes from the nozzle, will have a high velocity, which gives them the momentum. So the sprinkler will also gain an opposite momentum, and that is why, or that is what is making the sprinkler to rotate. That way it is able to spray the field in the garden. Then from there we have the assignment number 4. Again, make sure that you practice a lot before you attempt the assignment. So thank you, and let us meet in our next lesson.